Okay, so for today we will be solving one of the problems in LRU Cache. As you can see, I've already solved it before, but we will try to do it like from ground up without putting this. I really want to see my my thought process, like evaluate that piece of the puzzle. Uh, the my core intuition is in the in for an interview from experience, if you don't freeze in the first 10 to 15 minutes, you can code your way out of the problem. So for that, you have to be really good at kind of uh, brute forcing the solution. Because once you have like something to work on, you can really like the interview really helps. But for the first part, I think I'm missing. I get nervous, to be honest. So let's see what we can do about it, and we will try to solve this piece. I've done it before, but uh, not recently. Okay, so the problem basically asks us to implement an LRU cache. LRU cache is basically uh, least recently used eviction. Okay, so if the cache gets full, we just delete the least recently used one. Uh, so the core problem will have this piece in the cache class get piece of the puzzle. The key exists. Otherwise, m-1 input. Update the value of the key if the key exists. The device add the key value pair to the cache. Okay, an update operation. If the number of keys exceeds the capacity from this operation, delete the recent key used to one. Uh, the function get input must each running off one time. Okay, so first of all, since this is problem one, capacity is the main right. Okay. Memory size. Equals 2 to the power 4, value is 10 to the power 5. And this is most to get input. Okay, we will for if I need later on problem, if I need to think about like further optimization, then I will think I will look into these, like doesn't integer or long something like that. Okay, but for now, for the code problem, let's quickly go through the example. So instantiate, then put one, returns nothing, right? Yeah, and then after the triplets, we have get one is there, so we will get one. And now this one is the okay. Let's try to track it quickly. Okay, because I think this piece helps when I'm problem solving. Maybe that this helps. Okay, so I really don't remember how I solved that. I have to know what's going on with me. Oh, yeah, I started 9:45. I'm gonna time myself because in interviews, I don't get more than like 40 minutes to go. Uh, so that's the point. That's more to okay. So we were forget, we are getting one, and now the least, sorry, now one, right? So the most recently used one becomes, memory becomes one. Right? Yes, at this point, for after the first get, MRU becomes one. Then who's good at using whiteboard? Yeah. What? Um, okay. So LRU and okay, it's gonna it's flow. So my most recently used becomes one, and later on in the problem we will do three three since our cache is already full with one and two. Okay, let's say we have another one. Yeah, we do it properly. So LRU is over here. We will have okay. The main cache is this one. Okay, so we already have two values over here, and uh, those are basically okay. The what do I write on this one? That's a bit spelled there. Oh, yeah, one. So we had one, two, uh, and for the most recently used part, we have one. Then from where did it come from? Okay, from here. We get from here. And from 3, 3, like we want to put 3 again. But look at the problem. We can't do that because our cache is already full with 2. So we have to evict 1. This is one of the eviction scenarios. And the way we would do it is what's the least recently used? Then MRU is 1. So least recently used was 2. In that case, we will, since least recently used was 2 and MRU was 1. So first of all, if I'm explaining it to someone, I have to be really specific. We have basically LRU. We would have two pointers, LRU and MRU, most recently used and least recently used, and they will keep pointing at it's gonna be something like they will be all constantly pointing to some uh, value over here, like one or two, and that's how we will track it. Uh, I remember that part because at any point I would have to know about these two things for the eviction scenario. But as we were doing a rough breakthrough for put, when I'm doing the next put, like this one, three, three, I would have to evict the least recently used two and put three here, right? I'm gonna do three here. Yeah, it was the next two. Cache is one and three. So cache is currently one and we will have three if it's easier. Okay, so we have one, three. Our LRU is currently oh yeah, I remember that part. Okay, so after each operation, these two will get uploaded. So our cache is kind of like this, one, three. Either you and think about like either you're pointing at something right now. But for the brief overview, I would say keep track of the problem. Either you cache dot put for four. You have to check which one was recently used. Because I remember three was last used. That's our most recently used. And least recently used in that scenario becomes one. So we will evict one and then yes, evict one and then put what do you call it, four. So our cache now contains three and four. And in my view, most recently used one was four, our get operation, sorry, output operation, and least recently used becomes three. That's it. So from this problem, yeah, returns three, returns four. So from this breakdown, um, I remember a core in philosophy while solving it for the first time. This this problem becomes way easier if I think in terms of linked lists. Because think about it, we have a few nodes to work with. They will have their own key values, and we have to constantly maintain the position. So LRU keeps pointing at maybe three, four at some point, right? So at some point, points at three, points at four. It's way easier to just maintain a linked list with pointers and keep pointing different nodes, other than doing any other rough data structures in here. But let me just quickly think what brute force solution I can come up with, because I have an intuition for the main problem that I learned. But for brute force, if I'm given such a problem, a cache problem, what would be my initial take? I would have like till five to think about, and then like 10 or five, and then I'd start the problem. Uh, why not maintain a queue? Because we know like queue is well, first in, first out. So we would have something popping in and like something that's pushed um, this way out. So first we will have like two's gonna go out, then one, sorry, one, two, then we'll reach the capacity. So popping. So why not this way? Let's think about it for a few minutes. If I'm going forward with that philosophy of using a queue, what are the four issues I will walk into? First is I can still maintain looking at the least recently used, most recently used thing via these pointers. I can have like two pointers and point at different things while I'm using a queue. But I think the main problem would be we will have um, the order. I think the order is gonna be the biggest issue because once I like for example if you have like if something happens I have to like if I'm getting some element or if I'm like putting some element like four, three, blah blah blah, eight. If whatever I'm doing for this whole usage, order is pretty important. And what I mean via order is when I'm doing an operation, like I'm inserting one or deleting two, every time at each operation, the whole design changes. And a queue wouldn't basically give me that flexibility of like, what do you want me to do? Like create a new queue every time? That doesn't work. Uh, so this is, I would say, sufficient to nullify that argument that don't use that kind of data structure. Uh, other than that, let's think about what are the other things we can come up with. Um, when I'm using these two pointers, okay, so that's like one piece of the puzzle of why I wouldn't. Uh, I wouldn't use queues, but I think we can now get started with the main problem. Okay, so that's gonna be the main solutions. Okay, so I think I'm good on time. First of all, we would have, since we just fixed our kind of design pattern, like we'll be using linked list, I think maintaining the order becomes easy because, as we know, with a linked list, deleting and inserting a node is like really convenient. If I want to delete this one, just point it to this, point this to this, and everything is done, right? So that piece of the puzzle becomes easy, but the core iteration is order, maintain the order after each operation. There's no questions about it. So let's say we would have two pointers, LRU and MRU, and these two will be pointing to different elements in the. Okay, so we'll have this kind of scenario, and one, two, time. And the reason I'm using a key value pair here is the problem. So I should have like called it out earlier. When it says given but must each running off one average time, that clearly hints me towards using hash map like off one time. It's no brainer. So that's why I will be opting to use a key value pair here. But can we? Yeah, I think that's good enough. That's good enough. We will be using a key value here. Column close. Yeah, I think that's it. But how do I use key value pair? Let's do it again. Okay, so suppose we have a key value pair here. So is like what? One value is one. Then values two and this two. And let's think about the problem now. So we have LRU and RU, the hash map ready. So do we fit the hash map in with step what I'm thinking? Because this whole thing, can we just use this in here? Ah, what? You know, if I did with it. So getting back to the design problem, how do I fit this inside? Okay. Mhm. So tab. Oh, okay. The catch was for the key value pairs, since we would have to update it every time something happens, it's kind of more convenient if instead of the value, I just point it to the main node. Oh, okay. Now everything's falling into place piece by piece. Okay. So let's build up my let's review like to try to build up our intuition. So whenever we are doing, well, like we will have, so think about this. We have a basic structure, right? And whenever we are inserting or deleting, like whenever we are doing get operation or put operation, we would be messing up the order, right? Because most recently use and least recently use changes after each operation as per the LRU cache logic. So for get and for put, we would have to update the situation, update the whole linked list, and evict if needed. So that's like given. We have to. But every time, if I just have the whole value here, so after each operation, I would have to change both the linked lists and hash set. So the way we can the way we can think about it is using using a node or using a unified design. Okay, now it makes so much more sense when I'm talking through it. So I remembered using a node for this problem. Uh, so the node basically will have what key values, mm, value, and then we'll like uh, link this basically uh, and prep. But if I didn't do it here, like if I didn't have a node here, we would have to fit in the whole freaking hash map inside, and every time I changed something, I would have to basically access the map and then uh, change the operation. Then change the value for maybe for get will change for put will change the value. So access the hash map and then change it. And that's kind of really bothering the way we can bypass all that different problem is using pointers instead. So suppose, so remember this node, when okay, then I'm going to the next part, I would be really specific. So suppose this whole thing, key value maximum pref, this whole can be moved. This is our node. So each of this is an object of this class. Okay, so these are all modules. So at the end, what do we have? We have our auth. We have our LRU. We will have nodes, and then these linked lists keep following, and we will also then have an argument, right? So that's kind of the problem. But when I'm doing that, I would also I would also need to make sure that I have like these things and I have access, off-on access. Uh, that off-on access will basically come from my linked lists. No, my hash map. So let's say we'll do let's look here, then value here. It becomes one. So these are our nodes. So don't care about like these are this same big ass structure the being sits up there. So that's these are the things. So two the way we would be pointing is we would instead of having the values as one, two, or whatever that is, we would be using pointers to this structure. And that basically would allow us to access and modify the nodes with minimal operations. And I'm really spending a lot of time here explaining the what because this problem has so many loopholes like intuition, I don't know, that goes. I think we're in a good shape, but I don't know if it kind of makes sense why instead of using a simple queue for cache, um, like using this folded structure. Because node is there, node is closure, and volume. Okay, so let's get started with the problem. So as I mentioned, we would have a separate class. So let's start with that one. So class node becomes what? What are the things we would have? First key, then we would have value, then we would have pointer. Let's use next. Compare with Joe's. Right. So after that, we'll have instructor, which is the sensitive box. Oh, okay. Let's say you have the node. So let's go to node folder. We're typing one folder. Um, where is the folder? Once we have this piece, oh, sorry, it's a class. It's members are by default not accessible, so we would have we use a public access modifier so that we can grab the values. So once I do that, uh, what can we do? First of all, let's try to break it down in smaller problems. We would have nodes of this. Each of them would be a node over here, right? And we can also make this a node like double. Who cares? So these are all nodes. We need to make this, to move forward. We need hash map. So the hash map, let's say, would we would have to use it across the whole frame. So let's do the private and say on regulate. Well, we would have this first. Let's say now. So we have it. Yeah, let's get started. Oh, we would need the capacity here input. So to access that, we would need. So that then what is the capacity? We can use cat over here. Okay, think we're good. So to get started, initially what we would do is make a new node, right? Let's say oh, we would need dummy nodes throughout the problem so that we need node pointer, LRU, node pointer, and R. So we would have LRU is equal to So, and then you can just have, you know, this LRU in on that is equal to LRU. So this whole linked list situation should be sorted after this. Recipe store, we have the two nodes set up. Recipe store with the two nodes set up. It's linked. We would, at this point, we would just insert new values. And so for that, let's say if, we can tackle the next piece, get if that dot find key given us not for the dash dot one that is that doesn't exist, then that's the return the key exists. Okay. So cache dot find key, if it exists, is not for the cache dot end. So the iterator didn't get go through that end before that it found it. So that means the element doesn't exist. If it exists, then return the value. Return. Oh, sorry. Okay. So if it exists, then that know the input is not found when node is equal to not found to node is equal to the node you first prepare is integer is a put. Oh, okay. So this, okay, yeah, look at the problem here. This is our key, which is basically an integer, the main key that we got. But value, as we decided, is a pointer because we don't want this whole actually over in like in there. So this is a pointer to the node. And what happened with the cache? Only an ordered map, and our node becomes the value at that key. So that's basically cache key. We have that thing. Okay. We already have the product. We have the node here. Then we would just do node value. We're good. And if it's not there, we would turn -1. But as I mentioned, what's the next step? We grab the node, our order things, right? So which one we have to think about the order. So we can basically remove that node. So we have a helper function remove node and we pass it. And then, oh, okay. Okay. This piece is kind of good. I don't know about it and then explain what I'm doing. So suppose we have this whole puzzle up here. Okay, so I can start to cut this down. Ah, it's better to cut. Okay, I will just explain it over here with a different, okay. So think about, so when we have this situation, yep, this situation, like LRU, least recently used, most recently used, and this is a point in time, a snapshot of what happened. And after that, I did get one. Since the value is of for that key, one is one, we would our function should return one. But what happens at that point? That's the most recently used part, right? So in the RU, like one has to go here. It can't stay as the least recently used one. It will be the most recently used one. And the way we can do it is deleting it. I wouldn't say delete, but like removing it from the linked list, and then just pulling it up here. So basically, we have the whole trail LRU, then 2, 2, and 1, 1, and they after that, like the same old most recently used. But we would have to do this piece of the puzzle every time for any operation that happened, because we would have to maintain the LRU and MRU pointers correctly. And the way we would do it is using these two operations, remove node and insert node, using basically linked list or functions. Uh, mm, hmm, I'm not going to talk about these right now because we shouldn't be that big of a problem. So we have remove node doing something, then we would have insert node, node. Okay, so even if things we need to tackle, but I will really not worry about it right now. We have this whole infrastructure set up, and after that, let's try to move on to on piece, which is the put scenario. So for put, if the batch the same cache time is not equal to what cache dot end for that. If that happens, then what it was the key does exist. So if it does exist, I would tag to doesn't exist right now. Okay. Don't exist right on the cache the situation, then we'll just put it. So we will have a new node. So we new node. Let's call it node pointer node is equal to new node with and value. After that, the key doesn't exist. We created the new node. We would just insert it to the insert node. Um, One thing I have to be really careful is it took me a while to figure that out. Whenever I'm doing the insert operation, insert node, bruh, I wouldn't be wasting my time of course. So what I basically wanted to say is whenever I'm having a bunch of these things, Since my pointers are always my LRU pointers are always at the edge, like LRU and and MRU at the edge. Uh, any point in time, if I get this node, I would remove it from the linked list. Uh, and when I remove happens, think about when I remove this node, what basically happens at the core is this one points to this node points to this, and since I did a get, I didn't like my core at its core for the linked list, only the order should change, right? The hash map won't change because I just did a get operation. Why would I change it for? Why would I touch this place? There's no point in modifying the hash map. I would just reorder it. So I would remove it from the linked list and put it next to the most recently used one. So our uh, one will show up here, right? Next to here. So there we will have 1 1 and MRE pointer. So that's kind of well, it's cool. It's kind of important. Okay. Let's see, smart plot. Okay. But so we will insert it and then there's nothing to return. Else, what does it mean? Means that it does exist. Okay. In that scenario, we would update it. So let's grab the node list. Node pointer node is equal to the way we did it last time. We put cache key. Then we would change the value. Nodes val is equal to value. And since I access this one, so I would do move node and insert node. So basically what I'm doing is you can see the same pattern we used up here. Um, Suppose this one was the piece, it already existed 1 1, and we wanted to change it to 1 3. So what we would do is uh, okay, grab that node, grab this piece, and update the value. We did 1 3 instead of 1 1, and then we removed it from the existing linked list and did the update operation here so that our 1 3 is currently that node is currently here. And since we are using node pointers, we don't literally have to maintain any other structure other than where's the node piece I had other than this chunk. So as of now, the only liability is this node object. Okay. So we're really tight on time. Uh, my target was to wrap it in 5 minutes. If you know. Okay. Once I do that, we would have after this works fine. We have the node, and it does exist. Since it does exist already. We grab the node. We updated the value. We go to the server. So that's basically it. And we would have to do like a maintenance work here if when cache is full after each update operation, put operation, we would see if our cache got increased in size because we can put new items. Forget we can't put new items, you don't have to do that check. But for this, we can if cache dot size is greater than cap, capacity, we would do do the evaluation. So for evaluation, what we would basically do is grab the node, which is node pointer node is equal to LRU next. That's the node that has to be okay. That has to be deleted. This node has to be deleted. Then we would just delete it. How would we do? How would we? Because it's a hash map. So we have to do two cleanup operations. Firstly, we would remove it from the linked list. I don't know what's happening here. Right, uh, we would do the linked list operation, like remove the node. Then we would also have to fix the upper piece, sorry, lower piece, the hash map piece. So this one was the linked list piece. Um, we would have to do hash dot units key as the hash map is accessed by key and yeah, we would have to use this key prediction. After that, okay, we have the key. uh, okay. And here we would do some house cleaning stuff. So we would have two nodes. The way we do is just basic this operation. Not function now. Controlling nodes. It's, and for deleting any reference, the pointers left next is right, right, this equal to left. Oh, let's think about it. Step function. We have LRU. Yes, yeah. Okay, we have oops. We don't care. We have three nodes. And the third to node. This node, we will basically point this to this, point this to this. Okay, we are fine with it. Then for the next insert node, it's basically the circle post. For that, what I can do is um, grab that energy copy about it. So here we have this situation most recently used. This is our request that keeps going. But this is the one I want to access. Oh, I don't want to delete it. I don't want, sorry, I don't want to remove it, but but what I basically wanted to do is in conclusion. Um, the other node that I have, for example, this, I want that to fit in here. So instead of the pointer being most recently, that this is the before situation, the after situation that I want is this. LRU points to the new node, and this whole left body at the left points to this, just extending it. So, and like blah blah blah, don't want to that. So let's say x plus node pointer was part right is equal to, let me call it is equal to uh, first able use first, then routes next is equal to now route is equal to right. Then we would also have nodes next is equal to MRU, MRU's squared is equal to no. Oh, minus okay. No, that's yeah. I think that the item should be good. Let's item. Okay, what happened? For the first get operation, I'm getting -1. Why? Well, let's set it up properly. At that point, the key doesn't exist, so this node will work. No, so you can think about it. Don't that at that point the cache is empty, and it doesn't have the because the cache dot point key. When the reach cache dot have, and then we would just make a new pointer where the key value inserted into the node. And also, we have the node from that right. Slash what is your key? Use key. That is the value is equal to no, which is a node pointer. And then let's try. Then it's not the free. The feeling of the free. Or now, just do the work that's slip is a portion. So that there's that. Now, two. We have to. Oh my god. Instead of -1 that means our get operations and output operation with two three still wrapping so the key does exist. So since the key does exist, I don't have to modify the cache size with this. We'll just grab the key, monitor the value, set up like just like this. If cache dot size is better than capacity, we would grab to this recently is fine. You know the for the term more rectangle list. So I can see that to this point at 4 and 5. So 3 becomes now plus within another put. At this point I expect my get since I'm cache dot size gets bigger. Size you get bigger. Then why couldn't I do it? Okay. Something you haven't done right now. I know I will stop it. Then to try it. Start. It's good. Bump into here, right? LRU's next. Eh, okay, is three values, three of known. Oh no. Okay. Okay, so let's see that. It's something from used to one. LRU. Was more value is three. This is the local value that we were talking about. Because I think this part is working fine. This is working. Let's check. We might do more. statement. Let's see. Let's see. Hotspot. Yeah, we have this one was to release recently used and the emitting was to limits to caches point two. Oh, so this is working fine. That's fine. And the next get your cancel find key. That key is like oh, this was one. Let me forget. Seriously, no, you're wrong. It's one. Caches for dot three. Let's think about the whole flow. Let's see. For if that key doesn't exist, we could reaches the end. We would create a new one, insert it and modify the cache. Else, we don't have to create a new one from scratch. We can access the node, update the value, and then call it a day. Updating the order carefully because we're gonna have to remove the node here because there's the human being. But yeah, I think that's just exists, you have to remove the node. Okay, what I'm basically trying to do here is like see the cache. Let's not really see the cache. There's Since I'm getting, okay, see, I should have got one here, right? Let's think about it. So, I should have got one here, but I got two. What is it mean? That in the prior step, something wrong happened. I want to track the first word, sorry, third word. That we expect around this, which is something wrong. This is not language. So, under input, like one is here, and the product will be, and this operation will bring this operation to 10. After that, we should have received erased once the cache is full. It doesn't matter that You know why? Because for the third part, we should have just stopped here. Think about it. Getting one. We won't stop here because cash is not small enough. We're go inside this development. I think I see the problem what happened. Okay. Here, we're just randomly deleting the key. But at its core, what is the key? Sorry for all the silent debugging. Um, key is the integer, right? Use the integer. Yep, such a bad code. Optimize it on but to clear the situation, while we were deleting it, we were using this key and that is not always right. So suppose if we have a new element, right? If no, about it. Suppose what could be the scenario that they're different. So when I'm doing a new key, then it's created was value cache key, and this key is same as the value nodes key. But for situations when we will it's not new, we're just updating it, then that build up a better solution just being unknown because for me it was afraid that they might what I basically thought was they might not going back to the same element, but cache dot index. Oh, there's no way. This is this is not the key. Okay, it makes complete sense. This is not this key is not the key that we are deleting though. It's the 11 nodes key. It's very obvious. I think now we're good to could have just used node here. Um, Yeah, that's it. An hour and what? 25 minutes. Oh,